So, good day everyone. Today I'll be discussing to you the topic 4.2, which is the environmental concerns and crisis, and focuses more on waste management. So, my name is Jerlina Caros Villanueva, and together with me is Chiris Agsinao, John Patrick Oropa, and Abigail Samson. So, since the beginning of humankind has been generating waste, but with the progress of civilization, the waste became of a more complex nature. All creatures, humans included, constantly make decisions about what to use and what to throw away. A chimpanzee already knows that the inside of the banana is good and that the peel is not and throws it away. The challenge for society is to minimize how much waste is generated and to convert waste into a resource. So, as a student studying environmental engineering, it plays an important role, and the essence of the waste, the zero waste concept is also important. So, waste management, also known as managing waste, waste is any material unused and rejected as worthless or unwanted. It is useless or profitless activity, using or expending or consuming thoughtlessly or carelessly. Waste management is a system of an organization that uses to dispose, reduce, reuse, and prevent waste. So there are three classifications of waste management: solid waste management, hazardous waste management, and lastly, radioactive waste management. So what is solid waste management, or what is solid waste? It is a non-liquid, non-soluble materials ranging from municipal garbage to industrial waste that contain complex and sometimes hazardous substances, where solid waste management is a management system to utilize solid waste in the most effective combination of management options to handle waste or waste streams within the confines of applicable regulations. So, such solid waste are often called municipal solid waste, or MSW, and consist of all the solid and semi-solid materials discarded by a community. So MSW comes from residential, commercial, institutional, and industrial sources. MSW, residential waste constitutes the bulk, which is 56.7% of MSW, and includes kitchen scraps, yard waste, paper and cardboards, glass bottles, plastic containers, and even sandbags. Then, for the commercial sources, which include commercial establishments and public or private markets, contribute 27.1% of each. In some regions, about two-thirds of commercial waste come from the latter, and institutional sources such as government offices, educational and medical institutions account for about 12.1%, while the remaining 4.1% are waste coming from the industrial or manufacturing sector. Based on available information from the regional state of the Brown Environment Reports and various WAC's data, the typical composition of MSW in the Philippines is shown that disease vectors are the means by which disease organisms are transmitted through air, water, and food may all be vectors. The two most important disease vectors related to solid waste are rats and flies. So therefore, the relationship between solid waste and human disease is intimately are obvious but difficult to prove. If, for instance, if a rat is sustained by an open dump and that the rat sustains a flea that transmits murine typhus to a human, the absolute proof of the pathway would require finding the particular rat and flea, and obviously important impossible task. So, the characteristics of municipal solid waste involves gross composition, moisture content, analysis of particular size, identification of individual component that makes up the MSW, and the density of solid waste. So refuse management depends on both the characteristics of the site and the characteristics of MSW itself. So MSW produced in domestic household is also known as refuse. So sometimes refuse management or municipal solid waste can be have the same meaning. So gross composition may be the most important characteristic affecting MSW disposal. And moisture content expressed as the mass of moisture per unit mass of wet or dry material. Then the particular size is the distribution, which is particularly important in refuse processing for resource recovery. For mechanical separation, such as using Trommel screen and magnetic separators. The fourth one would be the chemical composition of typical refuse uses both proximate and ultimate analysis in the combustion of MSW. Then lastly, one of the characteristics of MSW is the density, which varies greatly in geographic locations, seasons of the year, and length of time of storage. Collections are facilitated by using the containers that are emptied in the truck with a mechanical or hydraulic mechanism. So these are the different transportations that are used to collect solid waste. For instance, the garbage grinder, the kitchen garbage, the transfer station, and many more. So processing and beneficial use. Processing reduces the volume of materials to be landfilled and can create products such as fuels, oils, and steam for electricity generation. And the significant use means the reuse of solid waste as a substitute for raw material in manufacturing, as construction material, or fuel as a fuel, or as an ergonomic soil amendment. So the solid waste problem has three facets: the source, collection, and disposal. So the first is perhaps the most difficult, and a new economy of reduced waste, increased longevity, instead of planned obsolescence and thriftier use of natural resources is needed. So for one of the subtopics of solid waste management would be the solid waste disposal, wherein the disposal of solid waste is defined as the placement of the waste so that it no longer impacts society or the environment. The wastes are either assimilated so that they can no longer be identified in the environment as by incineration to ash, or they are hidden well enough so that they cannot be readily found. So solid waste may also be processed so that some of its components may be recovered and used again for beneficial purposes. So it is regarded as the least preferred method of managing solid waste, although it plays an important role in dealing with residual waste. There are only two realistic options for disposal. They are disposal in the ocean and on the land, and the environmental damage done by the ocean disposal is now understood. So the term sanitary landfill was first used for the method of disposal employed in the Bureau of Waste Ammunition and other material after World War II. So sanitary landfilling is one of the methods of solid disposal. It is the compaction of refuse in a lined pit and covering of the compacted refuse with an earthen cover. So typically, refuse is unloaded, compacted with bulldozers, and covered with compacted soil. This is the photo that is shown here is the arrangement of cells in an area method landfill. So cells are built up units of the landfill. They are called cells. So another method of solid disposal is the sitting landfills, which is rapidly becoming the most difficult stage of the process since few people wish to have landfills in their neighborhood. In addition to public acceptability considerations include the drainage, the wind, the distance from the collection, the size, rainfall patterns, soil type, depth of the water table, treatment of leachate, and proximity to airports. And lastly would be the ultimate use of the sitting landfills. In modern civilization, however, there is no longer possible and adequate disposal in becoming increasingly difficult. The disposal methods discussed in this chapter or in this topic are only partial solutions to the solid waste problem. Another solution would be to redefine solid waste as a resource and to use it to produce usable goods. And this idea is explored in the following slides. So the defining object of solid waste disposal as the placement of solid waste so that it no longer impacts society or the environment. At one time, this was fairly easy to achieve. Dumping solid waste over city was also quite adequate. But again, the disposal methods discussed here are only partial solutions to the solid waste problem, and there are other solutions that could be implemented, such as the 3 Rs, which is the reuse, reduce, recycle. So these are the following references that are used in this topic. And
reuse, recycling, and resource recovery. So waste generation has increased exponentially with the rise of the population's economic situation and the materialistic nature of society. So this makes the selection of solid waste disposal sites becomes more difficult and problematic. So as a result, society's interest in reuse, recycling, and recovering materials from waste has grown. However, the differences between these three elements are oftentimes confusing and sometimes misused. So when we say reuse, it involves either the voluntary continued use of a product for a purpose for which it may not have been originally intended, or the continuous use of a product itself. So it is the act of taking old items that you might consider throwing away and finding a new use for them. So using resources in a new way once we have finished using them for their original purpose. So an example of this are these empty cans. So instead of throwing these items out, so we can think of a new way we could use it. So for example, we can use it as a plant holder, or we can use it as a utensil holder. So the second element is the recycling, which probably the most well-known and well-understood among these three. So it is the act of turning waste into a new substance or product in which the materials are carefully separated and will later be processed into other goods which will be returned to the industrial sector. So the recycling process requires the participation of the public, since the public must perform the separation step or the separation process. So there are two ways that can be used to increase public participation in recycling, which are the regulatory or democratic. So when we say regulatory, so the government has the power to dictate that only separated materials will be picked up on each household. However, in democratic countries like the United States, so they have limited success of this type of approach since it causes public resentment. On the other hand, the democratic approach appeals to the sense of community and to growing concern about environmental quality. However, householders respond positively to surveys about prospective recycling programs rather than their active participation in source or waste separation. So based on the survey results, this can be concluded that participation in source separation can be increased by making source separation easy. So an example of this is the Seattle, which is a city in Washington. So they have 100% participation in its household recycling program. So they have separate containers for recycling cart wherein very convenient shop for each household since you only need to put the containers in the recycling cart placed along the curb. So ang mga ang mga tigolekta na ang bahala na mag-pick up sa ilahang separated waste. So in the city of Albuquerque, so they sell large plastic bags to hold aluminum and plastic containers for recycling. So, however, these initiatives are costly for each household since each household must buy plastic bags which cost 10 cents each for just recycling purposes. So, no matter what initiatives a state or a city could make, so we can only say that a recycling program is a success or not through the availability of markets that would buy these separated recyclable materials. So for example, there is a tua, so there are markets that magbuy og mga recyclable materials such as mga junk shops. So it is a necessity that if na recycling program, it should be linked to a market for the recyclable materials collected. Otherwise, these materials will still end up in the landfill site. So now the question is, how can markets for recyclable materials can be created? So simply, this can be created by public demand. So the third element is the recovery. So recovery is using mixed waste refuse as an input material to create valuable products as new outputs. So there are various processing steps to create new material out from mixed refuse waste. So the material recovery facility or the MRF, which can sometimes ma-observe nato siya ng mga facilities in barangays or some of the school campuses. So the recovery of materials is commonly conducted in this facility. So recovering various waste materials is very crucial and separation step. And these processes realize the characteristic or properties of material na i-recover or i-shred. So, naatay separation process na maka-facilitate with decreasing the particle size of refuse. So, kung may refuse is rubbish siya. And increasing the number of particles and achieving a greater number of clean particles. So, ang first step in a solid waste processing facility for recovering material is the size reduction or what we call shredding. So, shredding is a brute force breaking of particles of refuse by swinging hammers in an enclosure. So, there are two types of shredders used in solid waste processing. So, na vertical and horizontal hammer mills. So, when we say vertical hammer mills, so, ang refuse waste ma-enter siya sa top sa hammer. At the center of this machine will rapidly continue to swing, allowing the waste to be shredded. So, for example, this video presented, so this is an example of vertical hammer mills. So, in horizontal hammer mills, so the hammer swing will be changed depending on the size of the product being shredded. So, ang speed sa hammer is dependent siya on the refuse waste being entered on the machine. So, another video is represented. So, it is an example of horizontal hammer mills. So, next is the shredder and performance design. So, the performance of a shredder is assessed by the degree of particle size reduction achieved and then compared with the cost in power and shredder wear. So, the particle size distribution of a non-homogeneous material such as the municipal solid waste, can express using the Rosen-Gromler distribution function, which expressed in equation number 1, where y is the commutative fraction of particles, n is a constant, and x sub c is a characteristic particle size. So this equation 1 can also be expressed as ln 1 divided by 1 minus y, or equal to x over the characteristic of particle size to the power of a constant. So we can see here in the left side of the screen the Rosen-Gromler particle size distributed equation. So in this sample, the n as a constant is equal to 1 and the x sub c is equal to 1.6. So this plot figure 1 may be made using a log-log coordinates. So often, ang shredder performance is specified siya sa basis of 90% of the particles passing a given size. So the conversion from characteristic size to 90% passing is possible siya by recognizing this equation number 3. So a semi-empirical equation also is used to estimate the power requirements for shredders that was developed by Bond. So this equation number 4 can estimate the power that must be required for shredders. So W, as noted, is the specific energy required to reduce a unit weight of material 80% finer than some diameter of L sub f to a product 80% finer than some diameter of L sub p. So where ang W sub I ani is the bond work index, which can be seen in table 1. So in table 1, mauni siya ang mga typical bond work indices. Each materials magdepende siya sa location. But in this table, kasagara ani is materials present lang sa Washington, in Washington. So the factor 10 here, this one, also corrects for the dimensions. So typical values of the bond work index for MSW and other specific materials are given in this table. So both this LP and L sub F, so they must be in micrometers. So an example here, so example number 1, so determine the power required for shredding the waste with the following particulate. So L sub P is equal to 2 centimeters, L sub F is equal to 30 centimeters, and the bond work index is 400. Also, i-determine po daw natin ang power for processing a 100 tons per day of waste. So the solution is using the equation number 4. So energy, denoted as W, is equal to the constant of 10 multiplied by the bond work index, which is 400, times 1 over the L sub P minus 1 over the square root of L sub F. So ang kaning L sub P and L sub F, since saka centimeters man sila, so we need to convert it into micrometers. So, mauna ni ang result, which is ang 0.02 times 10 to the 6th and 0.3 times 10 to the power of 6. So, calculate, so we can have this answer, which is 20.9183 kilowatt hour per ton. So, for the second question, kaning to determine the power for processing 100 tons per day of waste, so we can have the W i-multiply nato sa 100 tons per day, which is ang isa ka day is equal to 24 hours. So 20.9183 kilowatt hour per ton multiplied by 100 ton divided by 24 hours. So we can have now the power of 87.42 kilowatts. So, dapat dili na to malimtan na we should always convert the LP and LF into micrometers. For the general expressions for material recovery, so any separating one material from a mixture, the separation is termed binary. So when we say binary, it is either 1 or 0. However, if mag-separate ta og more than one material gikan sa isa ka mixture, then it is called polynomial separation. So this equation shows the binary separator, and the objective of this is the separation of the x fraction. So this first stream is supposed to contain only x component, but the separation is dili perfect, so it contains an amount of contamination of y component. So this is called na a product of extract. So the percent of x recovered in this first stream, which is the r x sub 1, may be expressed as this equation number 6. So in such cases where there has been no separation, so wala na separate ang x and y components sa mixture, so the stream will be called the purity of extract and may be defined by this 7th equation. So, however, if separator might extract only a small amount of pure X and more contamination sa Y, then the performance of a material separator is assessed by both recovery and purity. So, this may be characterized by an additional parameter called the separator efficiency. So, an example of this, so a binary separator, which is a magnet, is to separate a product, ferrous materials, from a feed stream of shredded refuse. So the feed rate to the magnet is 100 kg per hour and contains 50 kg of ferrous materials. So the product stream weighs 40 kg, of which 35 kg are ferrous materials. So the question now is, what is the percent recovery of ferrous materials, their purity, and the overall efficiency? So using the product of extract na formula, so given this numerical values, so igo lang nato taplak. So the product of extract is equal to x sub I over the x sub 0 multiplied by 100. So 35 kilogram divided by 50 kilogram times 100, so ma-crash out na ang units. So ang product of extract now is equal to 70%. So next is using the purity of extract. So x sub 1 divided by x sub 1 plus y sub 1 multiplied by 100. So we can have the purity of extract with 88%. So once nakuha na nato ang product of extract or purity of extract, we can now compute for the overall efficiency using the equation number 8. So simply 35 divided by 50 multiplied by the y sub 2 divided by the y sub 0, which is 945 divided by 950 times 100. So we can have now the overall efficiency of 70%. Screens can separate materials solely by size, so they do not identify the material by any other property. So screens are most often used in materials recovery as a classification step before a material separation process. So we have here an example of the most widely used screen materials recovery is the trommel. So the trommel has 3 different behaviors. So they behave in 3 different ways. First is the cascading, which naka-low speed lang siya, so they simply rolling back. Cataracting at higher speed, in which centrifugal force carries the material up to the side and it falls back. So the third way is the centrifuging, which has even higher speed, in which material adheres to the inside. So we have here an example. So find the critical speed for a 3-meter diameter trommel. So using the formula or the equation number 9, so we can compute now the critical speed. So given the 3-meter diameter, so di ba ang nasa formula is radius. So since diameter man ang given, we have to divide it by 2 to get the radius and convert it into centimeters. Since radius of drum must be in centimeters sa formula. So using the formula, so square root of 980, which is a gravitational constant in terms of centimeter per second squared din siya, divided by the 4 pi squared multiplied by the radius, which is 150 centimeters. So we can have now the critical speed sa 3-meter diameter trommel equal siya sa 0.407 rotation. So next is the air classifiers. So air classifiers, so materials may be separated by their aerodynamic properties. So in shredded MSW or the municipal solid waste, most of the aerodynamically less dense materials are organic, and ang denser materials are inorganic. So we can conclude na ang air classification can produce a refuse-derived fuel or RDF superior to unclassified shredded refuse. So here's a figure 3, which is ang air classifier. So we can see here the fraction is keeping with the airstream. So mauni siya ang tawag nato na product or overflow. But if ang fraction mo fall out of the bottom, so it is a reject or underflow. So there are two factors no nga maka-influence sa recovery sa organic materials by air classification. So first is not all organic materials are aerodynamically less dense, nor are all inorganic material denser. So complete separation thus organic from inorganic material can never occur regardless sa chosen na air velocity. So second is perfect classification of more and less dense materials is difficult because of the stochastic nature of material movement in the classifier. So next are the magnets. So fierce material may be removed from refuse using magnets, which continually extract the fierce material and reject the remainder. So isa ka example of a magnet na maka-remove siya of fierce materials is ang belt magnet. So it enhances the recovery of fierce material, but ang placement niya is maka-decrease siya sa purity sa product. So next is the separation equipment. Excuse me. So separation equipment as recovery operation evolve, more and better material separation and handling equipment will be introduced. So here naatay different examples of separation equipment. So this includes the jigs. So this is used for removing glasses, and then froth flotation for separating ceramics from glasses, and eddy current devices for recovering aluminum materials. Next is the energy recovery from the organic fraction of municipal solid waste or the MSW. So the organic portion of waste makes an excellent secondary fuel called refuse-derived fuel. So it can be used in current electric generating facilities as shredded and classified fuel, either as a fuel substitute for coal or as the only fuel in particular boilers. So this reaction here na makita nato is assumed siya as a combustion of organic materials. So it is composed of carbon dioxide and water. However, not all hydrocarbons are oxidized completely lang sa carbon dioxide and water. So there are also other components na mo-oxidize siya sa fuel, like the nitrogen and the sulfur. So once hydrocarbons are oxidized with other components of the fuel such as nitrogen and sulfur, so we can form these different chemical reactions. So, as we all know that ang nitrogen dioxide is important component siya sa formation sa photochemical smog. However, if maka-form ta, ay if ang particles is form siya into sulfur dioxide, so makadamage siya both sa human health and sa vegetation. How much more if ang sulfur trioxide reaction is ma-form. So, diri na ma-form ang acid rain. So, acid rain forms by the reaction of these chemical compounds. So, heat of combustion or heat value. So, ang heat value is a term used in engineering field. Heat value ang tawag. It is measured using a calorimeter and is expressed in SI units as kilojoules per kilogram or a British thermal units in British units or BTU. So here the table 2, makita nato ang mga typical values of heat of combustion either in SI units or in British units with different fuel materials or fuel compounds. So with that, it can be concluded that when addressing the solid waste problem, both source control and disposal must be taken into account. And as the waste continues to accumulate and disposal and becomes more limited and expensive, many reuse and recycling techniques must be developed. But unfortunately, we are still years and years away from the development and use of fully recyclable and biodegradable materials. But we should be mindful of our waste and we should learn to hinay-hinay adapt or maghinay-hinay na taog practice in reusing, recycling, and recovering our waste materials. So this includes my references for this chapter.
Topic 4. Environmental Concerns and Crises. Hazardous Waste Management. Over the years, the term hazardous has evolved in a confusing setting as different groups advocate many criteria for classifying a waste as hazardous. Different agencies use such descriptions as toxic, explosive, and radioactive to label a waste as hazardous. Hazardous waste is defined by the degree of instability, corrosivity, reactivity, or toxicity. This definition includes acids, toxic chemicals, explosives, and other harmful or potentially harmful waste. In this slide as shown, a classification criteria for hazardous with its corresponding description. Bioconcentration is the ability of an organism to accumulate a chemical from the ambient environment. For instance, a fish living in a river contaminated by pharmaceutical waste might intake high levels of human hormones from the water. Lethal dose 50 is a calculated dose of a chemical substance that is expected to kill 50% of a population exposed through a route other than respiration. Next is the lethal concentration 50 is a calculated concentration of a chemical substance that, when following the respiratory route, will kill 50% of population during a 4-hour exposure period. Phytotoxicity. It is the ability of a chemical substance to cause poisonous reactions in plants. In United States, more than 60 million metric tons by weight of hazardous waste generated annually. More than 60% is generated by the chemical and allied industry. The machinery, primary metals, paper and glass products industries each generate between 3 and 10% of the nation's total. Furthermore, in the Philippines, according to the JICA study on the hazardous waste management, approximately 280,000 tons of hazardous waste are generated each year by the officially registered 719 hazardous waste generators. Waste processing and handling are key concerns as hazardous waste begins its journey from the generator site to a secure long-term storage facility. Ideally, the waste can be stabilized, detoxified, or somehow rendered harmless in a treatment process similar to the following: chemical stabilization or fixation, volume reduction, waste segregation, detoxification, degradation, and encapsulation. For the chemical stabilization or fixation, in this method, waste sludge is combined with chemicals pumped onto land and then solidifies over the course of a few days or weeks. Pollutants like heavy metals may get chemically bonded in insoluble complexes, creating a chemical nest that traps the waste. Vast amount of diluted trash can be treated via chemical stabilization, which is an alternative to excavating and transporting large quantities of hazardous garbage. For the volume reduction, it is usually achieved by incineration, which takes advantage of the large organic fraction of waste being generated by many industries, but may lead to secondary problems for hazardous waste engineers, like air emissions in the stack of the incinerator and ash production in the base of the incinerator. Both byproducts of incineration must be addressed in terms of risk as well as legal and economic constraints. For the waste segregation, before any shipment to a processing or long-term storage facility, wastes are segregated by type and chemical characteristics. Similar wastes are grouped in a 55-gallon drum or group of drums, segregating liquids such as acids from solids such as contaminated laboratory clothing and equipment. Waste segregation is generally practiced to prevent undesirable reactions at disposal sites and may lead to economies of scale in the design of detoxification or resource recovery facilities. The next treatment is the detoxification. It is the removal of harmful or unwanted components from waste. Many thermal, chemical, and biological processes are available to detoxify chemical waste. Options include such as neutralization, ion exchange, incineration, pyrolysis, aerated lagoons, and waste stabilization ponds. These techniques are specific, particularly ion exchange. Obviously, it does not work for every chemical, and some forms of the heat treatment may be prohibitively expensive for sludge that has a high water content. Next is the degradation. Chemical degradation is a form of chemical detoxification. Waste-specific degradation processes include hydrolysis, which destroys organophosphorus and carbonate pesticides, and chemical dechlorination, which destroys some polychlorinated pesticides. Biological degradation generally involves incorporating the waste into the soil. Land farming, as it has been termed, relies on a healthy soil microorganisms to metabolize the waste components. So land farming sites must be strictly controlled for possible water and air pollution that results from overactive or underactive organism populations. And last technique is encapsulation. Hazardous waste can be encapsulated with a variety of materials. The standard 55-gallon steel drum is one option, but other materials like clay, plastics, and asphalt can be used to solidify the waste. Several layers of various materials such as an inch or more of polyurethane foam to stop corrosion are frequently advised for the exterior of the drum. Hazardous waste are transported across the nation on trucks, rail, flat cars, and barges. Haulers' major concerns over hazardous waste include operator training, insurance coverage, and special registration of transport vehicles. Handling precautions include workers wearing gloves, face masks, and coveralls, as well as registration of handling equipment to control future use of the equipment. The term hazardous waste manifest. The concept of a cradle-to-grave tracking system has long been considered key to proper management of hazardous waste. Copies of the manifest are submitted to generators and state officials so all parties know that each waste has reached its desired destination in a timely manner. This is an example illustration of a hazardous waste manifest. This system serves four major purposes. First is to provide the government with a means of tracking waste within a given state and determining quantities, types, and locations where the waste originates and is ultimately disposed. Second is to certify that waste being hauled are accurately described to the manager of the disposing facility. Third is to provide information for recommended emergency response if a copy of the manifest is not returned to the generator. And lastly is to provide a database for future planning within a state. Packaging. Packages in terms of design and construction are prescribed according to regulation, whether they are considered waste or usable materials. Corrosive material, flammable material, volatile material, material that if released would be toxic by inhalation, and any material that if released during transportation would pose a threat to human health and safety or to the environment must be packaged for transportation properly. And for the labeling and placarding, before any waste is transported from a generating site, each container is labeled and the transportation vehicle is placarded. Multiple labeling is desirable if, for example, a waste is both explosive and flammable. These labels and placards warn the general public of possible dangers and assist emergency response teams as they react in the event of a spill or accident along a transportation route. Accident and incident reporting. Accidents involving hazardous waste must be reported immediately. Accident reports that are submitted indicates the amount of materials released, the hazards of these materials, and the nature of the failure that caused the accident. And for the recovery alternatives, so this is based on the premise that one person's waste is another person's prize. So what may be a worthless drum of electroplating sludge to the plating engineer may be a silver mine to an engineer skilled in metals recovery. So in hazardous waste management, there are two types of systems exist for transferring this waste to a location where it is viewed as a resource. So first is hazardous waste materials transfers and hazardous waste information clearinghouses. An industrial process typically has three outputs. So first is a principal product which is sold to a consumer. Second is a useful byproduct available for sale to another industry. And lastly is waste. This is historically destined for ultimate disposal. Clearinghouse. So the pure clearinghouse has limited function. So these institutions offer a central point for collecting and displaying information about industrial wastes. Their goal is to introduce interested potential trading partners to each other through the use of anonymous advertisements and contacts. Clearinghouses generally do not seek customers, negotiate transfers, set prices, process materials, or provide legal advice to interested parties. It's one major function of a clearinghouse is to keep all the data and transactions confidential so trade secrets are not compromised. So clearinghouses are also generally subsidized by sponsors, either trade, or governmental. So often they are only able to operate in the short term. So in comparison with clearinghouse concept, a pure materials exchange has many complex functions. So unlike the clearinghouse, it is only has a limited functions. So a transfer agent within the exchange typically identifies generators of waste and potential users of the waste. The exchange will buy or accept waste, analyze its chemical and physical properties, identify buyers, reprocess the waste as needed, and sell it at a profitable price. The success of an exchange depends on several factors. Initially, it includes a highly competent technical staff is required to analyze waste flows and design and prescribe methods for processing the waste into a marketable resource. So there are five waste that are generally recognized as having transfer value. First is waste having a high concentration of metals. Second is solvents. Third is concentrated acids. And fourth is oils. And lastly, combustibles for fuel. Materials exchange idea or concept revolves on this saying or that one person's waste may truly be another person's valued resource. Hazardous waste management facilities. Citing considerations. A wide range of factors must be considered in citing hazardous waste management facilities. All of the relevant ologies must be considered, such as hydrology, climatology, geology, and ecology, as well as current land use, environmental health, and transportation. For hydrology, hazardous waste landfills should be located well above historically high groundwater tables. Hydrologic considerations limit direct discharge of waste into groundwater or surface water supplies. For the climatology, hazardous waste management facilities should be located outside the paths of recurring severe storms. Hurricanes and tornadoes disrupt the integrity of landfills and incinerators and cause immediate catastrophic effects on the surrounding environment and public health in the region of the facility. For the geology, it takes consideration that disposal or processing facility should be located only on a stable geologic formations. Impervious rock, which is not littered with cracks and fissures, is an ideal final liner for hazardous waste landfills. In ecology, ideal sites for hazardous waste management facilities are areas of low fauna and flora density, and efforts should be made to avoid wilderness areas, wildlife refuges, and animal migration routes. Areas with unique plants and animals, especially endangered species and their habitat, should also be avoided. Alternative land use, areas with a high recreational use potential should be avoided because of the increased possibility of direct human contact with the waste. And for the consideration of transportation, roads to the facilities should be accessible by all-weather highways to minimize spills and accidents during periods of rain and snowfall. In terms of socioeconomic factors, it ranges from public acceptance to long-term care and monitoring of facility. These are first is public control over the opening, operation, and closure of the facility, public acceptance and public education programs. Third is land use changes and industrial development trends. And fourth is user-friendly structures and recovery of project costs. And lastly is long-term care and monitoring. Incinerators. Incineration is a controlled process that uses combustion to convert a waste to a less bulky, less toxic, or less noxious material. The principal products of incineration from a volume standpoint are carbon dioxide, water, and ash, but the products of primary concern because of their environmental effects are compounds containing sulfur, nitrogen, and halogens. The solid ash products from the incineration process are also a major concern and must reach adequate ultimate disposal. Several basic considerations in the design of an incinerator for a partially combustible waste. First, the waste material must be atomized as finely as possible to present the greatest surface area for mixing with combustion air. Second is adequate combustion air must be provided to supply all the oxygen required for oxidation or incineration of the organic present. Third is the heat from the auxiliary fuel must be sufficient to raise the temperature of the waste and the combustion air to a point above the ignition temperature of the organic material in the waste. As we know, air emissions from hazardous waste incinerators include the common air pollutants. Inadequate incineration may result in emission of some of the hazardous materials that the incineration was intended to destroy. PCDD is the most potent compound of its series, polychlorinated dibenzodioxins, known as PCDDs or simply dioxins, and became known as a contaminant in Agent Orange, a trichlorophenol herbicides product. The acute toxicity of PCDD in animals is extremely high. However, in humans, the evidence for these adverse effects is mixed. Although acute effects such as skin rashes and digestive difficulties have been observed on high accidental exposure, these are transitory. Public concern has focused on chronic effects, but existing evidence for either birth defects in humans from chronic TCDD exposure is inconsistent. Regulations governing incineration are designed to limit TCDD emissions to below measurable quantities. These limits may usually be achieved by the proper combination of temperature and residence time in the incinerator. Landfills. Landfills must be adequately designed and operated if public health and the environment are to be protected. For the design, the primary system is an impermeable liner, either clay or synthetic material, coupled with a leachate collection and treatment system. A leachate collection system must be designed by contours to promote movement of the waste pumps for extraction to the surface and subsequent treatment. A secondary safeguard system consists of another barrier contoured to provide a backup leachate collection system. In the event of failure of the primary system, the secondary collection system conveys the leachate to a pumping station, which in turn relays the wastewater to the surface for treatment. A final safeguard system consists of a series of discharge wells up gradient and down gradient to monitor groundwater quality in the area and to control leachate plumes if the primary and secondary systems fail. Operation. As waste containers are brought to a landfill site for burial, specific precautions should be taken to ensure the protection of public health, worker safety, and the environment. Site closure. Once a site is closed and does not accept any more waste, the operation and maintenance of the site must continue.
Nuclear energy has effectively protected air quality since it generates carbon-free electricity. However, nuclear power causes a major environmental problem, such as the production of radioactive waste, and this radioactive waste is considered as an environmental pollutant. It has brought many hazardous impacts not only to humans but also to environment. This chapter aims to discuss the interaction of the ionization of radiation with the matter, as well as the discussion of radionuclides and the environmental implications of nuclear energy production which is the radioactive forms of elements that are accessible to humans in the environment. And also the impact of ionizing radiation on environmental and public health highlights the engineering options in managing and disposing of radioactive waste that is currently available. So in order to understand the concept of the ionization of radiation, we need to discuss, or we are going to discuss first the concept of radiation. So in the concept of radiation, a German mechanical engineer or German physicist, who is Wilhelm Röntgen, discovered the X-rays at the end of 1895. In conducting various experiments, he created the modern understanding of ionizing radiation. The discovery of Röntgen was followed by the observation of Henry Becquerel, a French physicist, who observed the radiation uh, has similarities to X-rays derived from certain uranium salts. And next is Marie and Pierre Curie. They studied radiation from pitchblende and chalcocite, which are uranium ores, and isolated two additional elements, which are radium and polonium, discovered and named by them. It is considered that the discovery and isolation of these radioactive elements marked the beginning of the atomic age. According to the magnetic field's direction of deflection, radiation derived from radium and polonium was classified into three types, and these are the alpha, beta, and gamma. Note that the sources and effects of alpha, beta, and gamma, as well as the neutron emissions, are essential, since understanding these factors or these things is required to manage radioactive waste. The next is Ernest Rutherford. He recognized the alpha particles coming from uranium as ionized helium atoms in 1905. And lastly is Sir James Chadwick. He characterized as neutrons the extremely radiation that comes from the bombardment of beryllium with alpha particles in 1932. The radioactive atom's unstable nucleus is transformed into one that is more stable through the emission of alpha, beta, or neutrons, and the release of additional energy through gamma radiation. After the radioactive atom loses energy by radiation, it is then transformed into isotope of the same element, which is either neutron or gamma emission, or an isotope of a different element, which are alpha or beta emission. This transformation or the emission of energy is in the form of ionizing radiation called radioactive decay. The rate of radioactive decay is also the decreased rate of the number of radioactive nuclei, which can be expressed by a first order rate equation. And this is the first order rate equation of the radioactive decay, where N is equal to the number of radioactive nuclei and K sub B is a factor called disintegration constant, which has a unit of time inverse. After integration, radioactive decay can be expressed as this formula. In the graph, as a radioactive sample contains several particles at time t, which is equal to 0, this number of particles will decrease slowly in an exponentially decaying manner. If you look at the radioactive decay equation, which is shown at the previous slide, which is the second equation, the number of particles depends very much on decay constant. Since the decay constant is large number, and the decay is going to happen very fast. However, if the decay constant is very small, the decay is going to happen very slowly. Another parameter which tells us about the characteristics of the radioactive species present is also known as the half-life. The half-life of any given radioactive species is defined in such a manner that it is a time in which a sample decreases to half its original number. As we can see in the graph, the time increases as the number of radioactive atoms decreases. For example, in T equals to 2 half-lives, N becomes 1/4 N naught. At T is equals to 3 half-lives, N becomes 1/8 N naught, and so on. For the ionization of radiation is the emission from radioactive nuclei that ionize in an atom or molecule when they collide with an atom or molecule. It is further characterized as alpha, beta, or gamma radiation by how it behaves in a magnetic field. As we can see in the figure, a beam of radioactively disintegrating atoms is aimed with a lead barrel at a fluorescent screen designed to glow when the radiation hits. Probes with alternating charges steer the alpha and beta radiation correspondingly, while the gamma radiation is observed as invisible light, an impeded flow of neutral particles passing through the electromagnetic field. The alpha and beta emissions are observed to have some mass and are considered particles, while the gamma emissions are photons of electromagnetic radiation which carry zero charge, zero resting mass, and travel at the speed of light. The alpha radiation is identified as helium nuclei. It has no direct health risk and is posed by external radiation from particles because even the most energetic ones are halted by the epidermal layer of skin and rarely penetrate to more sensitive layers. One material contaminated with alpha-emitting radionuclides is eaten or inhaled or might be absorbed inside the body, a health hazard will likely happen. While the beta radiation, it is the stream of electrons released at a velocity getting close to the speed of light. Interactions between beta particles and the atoms of pass-through materials are much less frequent than alpha particle interactions due to their lower mass. The slower rate of energy loss enables beta particles to move through air for several meters and human tissue for several centimeters. Internal organs are usually protected from external beta particles, except for exposed organs such as eyes. The assimilation of beta transmitters into the body may also harm a person exposed internal organs and tissue. For the gamma radiation, it is similar to X-rays. It is used in medicine, and this radiation is invisible electromagnetic radiation made of photons. The relaxation length determines the noticeably larger distance than gamma rays travel in all mediums. External doses of gamma radiation may produce significant human health harm since the dose is not greatly impacted by the passage of the radiation through the air. For the units for measuring ionizing radiation, ionizing activity causes harm which can damage living organisms since it can alter molecules within the cells of an organism. The damage is based on the quantity of energy transmitted to tissue by collisions with alpha and beta particles, neutrons, and gamma radiation. Extreme exposure to ionizing radiation may cause eventual harm and heat damage to the skin or tissue. The units for ionizing, to measure ionizing radiation uses the International System of Units, or the SI units, which measure the ionizing radiation, which is based on the meter kilogram second, and was established by the General Conference on Weights and Measures in 1960. These units are adopted upon the recommendation of the International Atomic Energy Agency. The SI units that are used in this chapter are the becquerel or the BQ, the Gray, GY, and the Sievert or the SV. The becquerel is the SI measure of source strength or total radioactivity. This is defined as 1 disintegration per second, and the units of becquerels are second inverse. The source strength in becquerels is not enough for full characterizations of source. The nature of the radionuclide and the energy and type of emission is also necessary. For the Gray SI unit, which measure of the amount of ionizing radiation needed to absorb 1 joule of energy per kilogram. of absorbent material. Historically, radiation absorbed dose was measured in rad. 1 gray is equal to 100 rad. The absorbed radiation dose is measured in grays. And lastly, the sievert is the SI measure of absorbed radiation dose equivalent. That is 1 SV of absorbed or ionizing radiation does the same amount of biological damage to living tissue as 1 gray or GY of absorbed X-ray or gamma radiation. The quality factors taken into account chronic low-level exposures as distinct from acute high-level exposures, and the pathway of the radionuclide into the human body, such as inhalation, ingestion, dermal absorption, external radiation, as well as the nature of ionizing radiation. For measuring ionizing radiation, there are 4 methods that are widely used to measure radiation dose rate, and the quantity of radioactive material present. And these are the following. First is the particle counter, which is designed to detect the movement of single particles through a defined volume. Next is the ionization chamber, which consists of 2 charged electrodes that are used to collect ions produced by corresponding electric fields. Next is the photographic film, which darkens after being exposed to ionizing radiation and serves as a sign of radioactivity. And lastly is the thermoluminescent detector, which are crystals that can be ionized to high electronic energy levels by radiation ionization. Chemical bonds are disrupted and electrons are ejected from molecules along the path of ionizing radiation, causing damage, which is the process of ionization. The interactions between these electrons and tissue molecules are mostly responsible for the biological effects that follow. The energy transferred during these collisions and interactions per unit travel length through the tissue is what we call the linear energy transfer of the radiation. The intensity of the biological harm increases with the amount of ionization seen along the particle's travel. Ionizing radiation can have somatic and genetic effects on living things. Somatic effects are consequences on individuals who have been directly exposed to the radiation that leads to sickness, such as circulatory system breakdown, nausea, hair loss, and sometimes death. And while the genetic effects caused by radiation damage to chromosomes have been shown to be inheritable in animals, but not in humans. As we can see in the figure, the dose-response relationship has been estimated to be linear at low doses and quadratic at higher doses. The extrapolated linear dose-response relationship is often referred to as the linear non-threshold theory of radiation health effect. There is evidence of a risk from ionizing, but it is modest and doubly unknown and dependent on a variety of conditions, and these comprise of the magnitude of the absorbed dose, the ionizing radiation type, the penetrating power of the radiation, the sensitivity of the receiving cells and organs, the rate at which the dose is delivered, and the proportion of the target organism exposed, and the possibility of a threshold below which there is no discernible damage. The sources of radioactive waste. There was no classification of radioactive waste until 1980. The United States Nuclear Regulatory Commission has categorized radioactive waste and other materials into the following groups. First is the high-level waste. Next is the uranium mining and mill tailings, the transuranic waste, byproduct material, and low-level waste. In the low-level waste, it includes everything that doesn't fall under one of the other categories. The following kinds of the low-level waste have been identified by the NRC to ensure proper disposal. And these are the following. First is the Class A, which only short-lived radionuclides and must be chemically stable. Next is the Class B, which has higher levels of radioactivity and needs to be physically stabilized before transportation or disposal. Next is the Class C, which is waste that will not decay to acceptable levels in 100 years and requires isolation for 300 years or more. and greater than less C, which are GTCC, it will not decay to acceptable levels in 300 years. And next, the mixed low-level waste. It is a low-level waste that contains hazardous waste as classified under the Resource Conservation and Recovery Act. And lastly is the formerly used sites remedial action program. For the nuclear fuel cycle, it generates radioactive waste at every stage. As we can observe in the figure, the waste produced by mining and milling activities is identical to that produced by uranium mining and milling. Mining and milling dust needs to be stabilized to prevent windborne dispersion and leaching into ground and surface water. Nuclear fuel is inserted into a core reactor where a controlled fission reaction produces heat, which in turn produces pressurized steam for electric power generation. Heat is removed from the nuclear reactor core, which is the primary coolant, through pressurized water, which puts the primary coolant under pressure and is not allowed to boil, or a boiling water reactors in which the primary coolant is permitted to boil. Through a heat exchange system that guarantees complete physical separation between the primary and secondary coolant, the primary coolant transports heat from the core to the steam system, or which is the secondary coolant. Condensing the used steam in the steam system requires a third cooling system, which draws water from outside resources. The primary source of radioactive waste in the nuclear fuel cycle is likely the nuclear reactor. For the reprocessing waste and other reactor waste, the term reprocessing refers to the entire process of extracting fissile material from irradiated fuel. Despite the fact that the special nuclear material is no longer being produced or extracted, the very large quantities of neutralized acid solvent sludge and the organic extraction solvents used contain high concentration of radionuclides and are classified as high-level waste. Through controlled leaks, the primary and secondary coolant in a nuclear power plant acquire significant radioactive contamination. Contaminants are taken out from the cooling water by ion exchange, and the loaded ion exchange columns are Class C or GTCC waste. Additionally, during ordinary nuclear reactor cleanup operations, Class A and Class B, waste are created. For additional sources of reactor waste, the increasingly widespread use of radionuclides in research, medicine, and industry has created a lengthy list of potential sources for radioactive waste. Naturally occurring radionuclides may pose harm to public health. By far, the largest fraction of background radiation ionization comes from radon. The combined dose of radon and its radioactive progeny can be significant when radon is inhaled. For the movement of radionuclides through the environment, a radionuclide is an environmental pollutant because of combination of the following properties. First is the half-life. Second is the chemical nature and properties. Third is the abundance. And fourth is the nature of the radioactive emissions. Like any other waste material, radioactive waste may contaminate air, water, soil, and vegetation. And this contamination may pose harm and affect the public health adversely. Doses of radiation from environmental contamination are usually classified by pathway, that is as inhalation dose, ingestion dose, and immersion dose. Radionuclides released and transported through air that people breathe enter the body by the atmospheric dispersion and inhalation pathway. Also, water transport occurs whenever radionuclides in surface or subsurface soil or on vegetation surfaces erode or leach into a watercourse, as well as when airborne radionuclides fall out on surface waters. Radionuclides also move from deposition or contamination of ground surfaces into the human food chain. For the radioactive waste management, the objective of the environmental engineer is to prevent the introduction of radioactive materials into the biosphere and particularly into the environment accessible to human activity for the effective lifetime of these materials. Next, the control of the potential direct impact on the human environment is necessary but not sufficient because radionuclides can be transmitted through water, air, and land pathways for many years and even for generations. Due to technological, political, and economic variables outside of their control, engineers in charge of managing radioactive waste must concentrate on long-term storage options or disposal. For high-level radioactive waste, a two-stage barrier system was developed by the U.S. Geological Survey in 1979 to minimize the leakage from the repository and dispersal of high-level radioactive waste to the environment. First is the waste from itself. This is the first barrier, which is radioactive material dissolved and dispersed in a glass matrix. The second barrier is the geologic rock formation itself. For transuranic waste, the Waste Isolation Pilot Project, or the WIPP, was found to be better suited as a repository of the transuranic defense waste than for the more thermally stressful high-level waste. The facility that is only operating geologic radioactive waste repository in the world is now receiving about 100 shipments of transuranic waste each month. For the low-level radioactive waste, commercial low-level waste, in contrast to high-level waste, has been under the control of the private sector since 1960. It has been disposed of without any treatment at all. The low-level waste is now being treated using methods such as impermeable packing, compaction, burning, and stabilization in an asphalt or cement matrix. For the transportation of radioactive waste, the blocking of all external radiation due to the high activity of radioactive waste will result in the difficulty of transport since it adds weight to the transport container. A regulation created by the Nuclear Regulatory Commission that a certain external dose called transport index should only be allowed to be transported. The container for the majority of the low-level waste must have undergone testing and certification to be able to resist the physical strains of standard transportation. The container must be able to survive specific accidents conditions, including mixtures of fire and mechanical stress for the high-level waste, for the transuranic waste, and some of the low-level waste.